SwayamPrabha. Digital India. Educated India.
Next, depth limited search. The embarrassing failure of depth first search is an infinite state space can be alleviated by supplying the depth first search with a predetermined depth limit L. That is, nodes at depth L are treated as if they have no successors. This approach is called depth limited search. The depth limit solves the infinite path problem. Unfortunately, it also introduces an additional source of incompleteness if we choose L is less than D. That is, the shallowest goal is beyond the depth limit. This is likely when D is unknown. Depth limiter search will also be non-optimal if we choose L is greater than D. Its time complexity is order of B power L and its space complexity is order of BL. So, the depth first search can be viewed as a special case of depth limiter search with L equal to infinity. Sometimes the depth limits can be based on knowledge of the problem. For example, on the map of Romania there are 20 cities. Therefore, we know that if there is a solution, it must be the length of 19 at the longest. So, L equal to 19 is a possible choice. But in fact, we studied the map carefully. We would discover that any city can be reached from any other city in at most 9 steps. So, this number known as the diameter of the state space gives us a better depth limit, which leads to a more efficient depth limiter search. For most problem, however, we will not know a good depth limit until we have solved the problem. So, the inbuilt function is function of depth limiter search returns a solution or failure or cutoff, return recursive DLS make a node, problem initial state problem limit, function recursive DLS node problem limit returns a solution or failure or cutoff. If problem goal test node state, then return solution, else if limit equal to 0, then return cutoff, else cutoff occurred false. For each action in problem, actions node state do, child node problem node action, result recursive DLS child problem limit. If result is cutoff, then cutoff occurred true, else if result is not equal to failure, then return result. If cutoff occurred, then return cutoff, else return failure. So, this is the inbuilt of the recursive implementation of depth limit tree search. So, depth limit search can be implemented as a simple modification to the general tree or graph search algorithm. Alternatively, it can be implemented as a simple recursive algorithm as shown in the figure. So, notice that the depth limit search can terminate with the 2 kinds of failure. So, the standard failure values indicates no solution, the cutoff values indicates a no solution within the depth limit. So, therefore, it is more advantage. Next, iterative deepening the depth first search. So, or it is a iterative deepening depth first search. In a general strategy often used in combination with a depth first search tree that finds the best depth limit. It does this by gradually increasing the limit, first 0, then 1, then 2 and so on until a goal is found. So, this will occur when the depth limit reaches D. So, the depth of the shallowest goal node, the algorithm is shown in the figure. So, the iterative deepening combines of the benefit of the depth first search and the breadth first search. Like depth first search, it is memory requirement or the modest. So, order of BD to be the precise like the breadth first search. It is a complete when the branching factor is finite and optimal when the path cost is non-decreasing function of the depth first node. So, the figure 3.19 shows that the 4 iteration of iterative deepening search on a binary search tree where the solution is found on the 4th iteration. So, the iterative deepening search may seem wasteful. So, the iterative deepening search may seem wasteful because states are generated multiple times. It turns out this is not too costly. The reason is that in a search tree with the same branching factor at each level, so most of the nodes are in the bottom level. So, it does not matter much that the upper levels are generated multiple times. In an iterative deepening search, the nodes on the bottom level are generated once, those on the next to bottom level are generated twice, and so on. So, up to the children of the root which are generated d times. So, the total number of nodes generated in the worst case is n of IDS, that is iterative deepening search equal to d of b plus d minus 1 into b square and so on b power d. So, that we can write the inbuilt function. So, the iterative deepening search algorithm is a function. Iterative deepening search returns a solution or failure for depth 0 to infinity do result depth limiter search problem comma depth. If result is not equal to cutoff, then return result. So, this is the repeatedly applies the depth limit search with increasing limits. So, it terminates when the solution is found, or if the depth limiter search returns failure, means that no solution exists. So, this is the way we have a limit 0, limit 1 and nearing search B and C. Once you searched B as well as C, then you have to put a block. Next, limit 2 going to do after B search D and E, and then E is final, then stop it. So, we have the block, bold block is mentioned in here, here and here, and then all the possibilities we have a root at. Similarly, if you limit 3 searches, so all these 3 searches and then B corresponding D and E, and B after D, D after H and I. So, we have a limit is 3, and then we have a bolded stop it. So, this figure corresponding to E to J and K, and then E to this you stop it. We have a 3 bold, and similarly and 3 3, that is 3 and then 3 3 like that. So, go ahead like this corresponding C to F and G and LM and go on. So, this is 4 iteration of iterative deepening search on a binary tree. So, make a note of that binary tree. So, which gives a time complexity. Therefore, order of B power T is asymptotically same as the breadth first search. There is some extra cost for generating the upper levels multiple times, but it is not large. For example, B equal to 10 and D equal to 5, the numbers are n of IDS equal to 50 plus 400 plus 3000 plus 20,000 plus 1 lakh equal to 1,23,450, whereas the breadth first search is equal to 10, 100, 1000, 10,000 and 1 lakh is 1,11,110. If you are readily concerned about the repetition, you can use the hybrid approach that runs a breadth first search until almost all available memory is consumed, and then runs iterative deepening from all the nodes in the frontier. In general, the iterative deepening is a preferred uniform. In general, the iterative deepening is a preferred uninformed search method when the search space is large and the depth of the solution is not known. So, iterative deepening search is analogous to breadth first search, in that it explores a complete layer of new nodes at each iteration. Before going on to the next layer, it would seem worthwhile to develop an iterative analog to uniform cost search. inheriting the later algorithm's optimal guarantee while avoiding its memory requirements. So, the idea is to use increasing path cost limits instead of increasing depth limits. The resulting algorithm called iterative lengthening search is explored. It turns out unfortunately that iterative lengthening incurs substantial overhead compared to uniform cost search. So, the idea behind bidirectional search is to run two simultaneous searches, one forward from the initial state and other backward from the goal, hoping that the two searches meet in the middle. So, the motivation is b power d by 2 plus b power d by 2 is much less than b power d, or in the figure the area of the two small circle is less than the area of the one big circle centered on the start and reaching to the goal. So, the bidirectional search is implemented by replacing the goal test with a check to see whether the frontiers of the two searches intersect. If they do, a solution has been found. So, the check can be done when each node is generated or selected for expansion, and with a haste table will take a constant time. So, for example, if a problem has a solution depth d equal to 6 and each direction runs a breadth first search one node at a time, then the worst case is two searches meet when they have a guaranteed. Then in the worst case the two searches meet when they have generated all of the nodes at depth 3. For b equal to 10, this means that the total 2220 nodes generation compared with 11,11,110 for a standard breadth first search. Thus, the time complexity of a bidirectional search using breadth first search in both directions is O of b power d by 2. So, this space complexity is also order of b power d by 2. Thus, the time complexity of a bidirectional search using the breadth first search in both directions is order of b power d by 2. The space complexity is also order of b power d by 2. So, we can reduce this by roughly half if one of the two searches is done by iterative deepening, but at least one of the frontier must be kept in memory so that the intersection check can be done. So, this space requirement is the most significant weakness of bidirectional search. So, this is the schematic view of the bidirectional search that is about to succeed when a branch from the start node meets the branch from the goal node. So, the reduction is a time complexity makes a bidirectional search directive attractive. So, the reduction in time complexity makes bidirectional search attractive, but how do we search backward? So, this is not easy as it sounds. Let the predecessor of the state x be all those states that have x as a successor. So, bidirectional search requires a method for computing predecessors. When all the action in the state space are reversible, the predecessor of x or just its successor. Other cases may require substantial ingenuity. So, consider the question of what we mean by the goal in searching backward from the goal. For the 8 puzzle and for finding a route in Romania, there is just one goal state. So, the backward search is very much like to the forward search. If there are several explicitly listed goal states, for example, the two dirt free goal states in the figure, then we can construct a new dummy goal state whose immediate predecessor are all the actual goal states. But if the goal is an abstract description such as the goal that no queen attacks another queen in the n queen problem, then the bidirectional search is difficult to use. So, in the figure 3.21 compares the search strategies in the terms of 4 evaluation criteria set forth in the section. So, the comparison for tree search versions for graph search, the main difference are depth first search is complete for finite state spaces, and that the space and the time complexity are bounded by the size of the state space. So, the criterion they are the the comparing for the search of breadth first, uniform cost, depth first, depth limited, iterative deepening, bi-directional if applicable. So, criteria is complete for breadth first is yes, For uniform cast both S and A and B. So, the A mean complete, B is a finite, and depth for speed no, and completeness for the depth limit is no, and completeness for the iterative depending is yes for the complete, and bidirectional if applicable both finite as well as complete, corresponding to complete. So, next time, so order of B per D for the breadth first, order of B per 1 plus floor of C star by epsilon, depth first is order of B power m, depth limited corresponding to time is order of B power L, and iterative deepening corresponding time criteria is order of B power D, and criteria time for the bidirectional is applicable is order of B power D by 2. Next, space criteria for the breadth first is order of B power D, for uniform cast order of B power 1 plus ceiling of C star by epsilon. Space for the depth first is order of Bm, space for depth limit is order of Bl, space for iterative deepening order of BAD, and then space for bidirectional if applicable order of B power D by 2. And next talk about optimal. So, breadth first is S for optimal, and uniform cast is also possible. For this depth first optimal is no possible, and then for depth limited is no possible, and for iterative method deepening optimal is possible, yes. Bidirectional is also possible. Here S power C stands for optimal if step cost are all identical, and S power C comma D both direction used for breadth first search. So, this section shows how an informed search strategy, one that uses the problem specific knowledge beyond the definition of the problem itself, can find the solution more efficiently than can uninformed strategy. So, the general approach we consider is called best first search. So, best first search is an instance of the general tree search or graph search algorithm in which a node is selected for expansion based on the evaluation function f of n. So, the evaluation function is consumed as a cost estimate. So, the node of the lowest evaluation is expanded first. So, the implement of the best first graph search is identical to that for uniform cost search. So, except for the use of f instead of g to order the priority queue. So, the choice of f determines the search strategy. So, most best first algorithm include as a component of f a heuristic function denoted by h of n. So, h of n is estimated cost of the cheapest path from the state at a node n to a goal state. For example, in Romania, one might estimate the cost of the cheapest path from Arad to Bucharest through the straight line distance from Arad to Bucharest. So, the heuristic function or most common form in which additional knowledge of the problem is important in the search algorithm. So, we study heuristic in more depth that section. For now, we consider them to be arbitrary, non-negative. We study the heuristic is more depth in the lectures. For now, we consider them to arbitrary, non-negative problem specific function with the one constraint. If n is a goal node, then h of n equal to 0. So, the remainder of this section covers two ways to use heuristic information to guide search. So, one is a greedy best first search, tries to expand the node that is closest to the goal on the grounds that is likely to lead the solution quickly. Thus, it evaluates the nodes by using just the heuristic function, that is f of n equal to h of n. So, let us see how the works for the root finding problems in Romania. We use the straight line distance heuristic, which we will call h suffix SLD. If the goal is Bucharest, we need to know the straight line distance to Bucharest, which are shown in the figure. For example, h suffix SLD in odd of equal to 366. Notice that the value of h suffix SLD cannot be computed from the problem description itself. Moreover, it takes a certain amount of experience to know that the heuristic SLD is corrected with actual road distance. Therefore, a useful heuristic can be designed. So, the figure 2.3 shows that the progress of the greedy best first search using S suffix SLD to find the path from Odd to Bucharest. The first node to be expanded from Odd will be Sibiu, because it is closer to the Bucharest than either Zirind or Timisoara. The next node to be expanded will be the Fagares, because it is the closest. So, the Fagares in turn generates the Bucharest, which is the goal. For this particular problem, the greedy best first search using H suffix SLD finds a solution without ever expanding a node that is not on the solution path. So, and each distance of the straight line Bucharest is found out from Odd to Zirind. So, Odd is 366, Bucharest is 0 because ending point, and Craiova 160, Drobeta 242, Euphoria 161, Fagares 176, and then Gurugio 77, Hirshova 151, Yazi 226, Lugos 244. Like that, the rest of the places also found and displayed on the figure 3.22. So, this is search cost is a minimal here. It is not optimal. However, the path through Sibiu and Fagares to Bucharest is 32 kilometers, which is longer than the path through the Rimini, Vilasi and Pitasi. So, this shows that why the algorithm is called greedy. At each step, it tries to get as close to the goal as it can. So, greedy best first search is also incomplete even in a finite state space, much like a depth first search. Consider the problem of getting from Iasi to Fagares. So, the heuristic suggests that Niamt be expanded first because it is closest to the Fagares, but it is dead end. The solution is go first to Vasuli, a step that is actually faster from the goal according to the heuristic, and then to continues to Udzensi, Bucharest and Fagares. So, the algorithm will never find the solution. However, because the expanding Niamt puts Iasi back into the frontier, Iasi is closer to Fagares than Vasily is, and so Iasi will be expanded again and leading to an infinite loop. So, this graph search version is complete in finite space, but not in infinite ones. So, the worst case time and space complexity of the tree version is order of B per m, where m is a maximum depth of the search space. With a good heuristic function, however, the complexity can be reduced substantially. So, the amount of reduction depends on the particular problem and on the quality of the heuristic.